Hi there. Let's review waves and tides first before I talk about ocean currents.
I feel like I'm at the ocean.
Except here, the waves are man-made.
Hi, Jacob and Catherine. I'm Dr. Hoffman from Old Dominion University.
Hi. This is a great place to do research.
We've been wondering, what is a tide exactly?
A tide is the regular rise and fall of the surface of the ocean due to the gravitational force of the sun and the moon on our Earth.
We learned that gravity is a force that exists between all objects.
And it makes objects fall to Earth.
That's right. And the bigger the objects and the closer they are to one another, the stronger the gravitational attraction between them.
The sun is much larger than the Earth and the moon, but a lot farther away from the Earth and the moon. So which one causes the tides?
They both do, but the moon plays the bigger role, being about twice as strong as the sun. As the two of them create a gravitational force on the Earth's oceans, it causes the water to move upwards towards the sun and the moon.
And the Earth's gravity holds the water down.
Right, but the tidal forces pull water sideways along the surface of the Earth, and this tug-of-war creates a bulge in the surface of the ocean.
If the moon's influence is stronger than the sun's, then is the bulge bigger beneath the moon?
Yes, and due to the rotational motion of the Earth-Moon-Sun system, there is also a bulge on the opposite side of the Earth away from the sun and the moon. These bulges of water are large waves that we call high tides.
So if the water bulges on opposite sides, then it must draw water away from the area between the bulges.
Very good, and that is where low tides occur.
How often do we have high and low tides?
Many coastal locations, such as the Atlantic and Pacific coast, experience 2 high and 2 low tides each day. But some areas, such as the Gulf of Mexico, only have 1 of each.
Do the tides in a particular place always occur at the same time?
No, but the answer is a little bit complicated. On average, high tides occur every 12 hours and 24 minutes. The Earth spins on its axis every 24 hours, so if you divide 24 by 2, you get 12. The extra 24 minutes is because of the moon's orbit about the Earth.
Would high tides help bring objects floating in the water onto the shore?
Tides do not typically have much of a role in transporting objects in the ocean. You can think of tides as a big sloshing motion where objects go as far in one direction as in the other. Here, let's check it out.
That was cool. But what about the waves?
Jacob, can you get in the pool?
Can I?
See the waves around Jacob? They look like they're moving the water forward, but actually they aren't.
How is it that I stay in the same place?
Each particle of water in a wave moves around in a circle. Energy moves forward while water particles remain in the same place, so an object floating on the water will rise and fall as the wave passes, but the object will not move forward.
I think we definitely need more research about waves.
Me too. Thanks, Dr. Hoffman.
You're welcome. Enjoy the wave pool.
Let's do one quick review question about waves before we get into surface currents. Or tides, sorry. So while walking on a moonlit stroll in the Bay of Fundy, you notice that there's a high tide, and it's at 2:15 a.m. At what time will there be another high tide? Well, let's look at our man again. We've used this image in our last lesson. So remember, the moon has the biggest influence on what's happening with tides. So let's say that this was at 2:15 a.m. And we get a high tide here, and we get a high tide here. So the Earth is rotating now, and in 8 hours, the guy's right there. A little more than 8 hours, the guy's going to be standing here, and he's experiencing another high tide. So that's about 12 hours and a bit. Back at the Bay of Fundy, it's going to be basically a little more than 12 hours. So always about 12 hours and approximately 24 minutes. That's approximate. So take this, and in 12 hours and 24 minutes we're going to get another high tide, which would be right there, about 2:40 p.m. Let's talk about ocean circulation and ocean currents. The movement of water depends on where we're at in the ocean. If we're close to the surface of the ocean, then water circulation mostly depends on the wind. Okay? However, if we're deep in the ocean, water circulation mostly depends on density. More on that in a minute. Let's talk mostly about the surface. The sea temperature looks like this if we were to take a thermograph of the sea surface temperature. If you notice, it's hottest along, of course, the equator. And it gets cooler, the surface, as we go away from the equator. Now, what do we know about unequal heating? Well, convection currents start when there's unequal heating. And a convection current is a wind. And so on the Earth's surface, we get winds that help push the water along on the surface. So here's our equator. And as you know, it's hotter here. So we got hot air rising off the equator. And as it gets away from the equator, it starts to cool and sink. And so this circular pattern helps push water also, like it does the winds. However, due to the Earth's rotation on its axis, in this direction it spins counterclockwise. What that does is objects tend to deflect in the northern hemisphere this way, and objects tend to deflect the opposite way. So if you're wind or water in the northern hemisphere, you tend to be deflecting and spinning in this direction, which is clockwise. And if you're in the southern hemisphere below the equator, you tend to spin counterclockwise. We call that the Coriolis effect. And how does this then affect things? Well, it helps affect surface currents. So again, here's our equator. And winds work very similar to this. Because of the Coriolis effect, or the spin of the Earth on its axis, what we do is we get hot water moving in this clockwise pattern above the equator. Clockwise. And we get water moving counterclockwise, like this in the southern hemisphere. Now, as you can see, geography plays a role in how these work too, because water obviously cannot go through continents or land. And so here's our normal pattern that occurs for surface currents on the water. So the Coriolis effect causes things to spin clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. So a surface current actually has a special name called a gyre, so massive circular system of wind-driven surface currents. They cover all the oceans, clockwise in the north, counterclockwise in the south. And so these gyres will help push things, like if you're an object in the ocean, it's not the waves or the tides that push you. However, these gyres will push you. So let's say you wanted to send a message in a bottle. Well, if you knew about surface currents, you could drop a message in a bottle right here, and it might end up over there in Europe, if you're lucky. The other thing that we talked about in regards to what is going on up below the surface is the following. The ocean has what's called a thermocline. A thermocline means that there's a certain depth where we get a huge change in temperature. And so not on the surface, but just below the surface, you get varying temperature changes. So starting right about here, which is about 50 meters below, all the way up to just below 1,000 meters, look at the change in temperature of the ocean. It's huge, and we can get currents, deep water currents, moving because of that as well, because the density of the water is changing, and so you get convection currents moving below in deep water. Here's a pattern of a storm, and you should be able to know what hemisphere it's in based on the following, based on the Coriolis effect. Remember, things spin counterclockwise in the southern hemisphere, and they spin clockwise in the northern hemisphere. And so that reviews again how surface currents work and the fact that the wind drives the surface currents, and deeper into the ocean where we have what's called the thermocline, we might get density driving the ocean currents.